Ladies and gentlemen, boys and girls and small woodland animals, my name is Marty Jopson, and this is a talk all about the most spectacular of the natural forces of the world. This is a talk all about electricity. This is a talk that aims to put the awesome back into electricity, or as I like to put it, the awesomosity, which is a word I coined especially for this talk. The awesomosity back into electricity, but it's also a talk that poses a question. The question is this: have we tamed electricity? Is electricity ours to do with what we will? It's a rhetorical question, young man. We will come to the answer at the end. But I like your enthusiasm. So yes, have we tamed electricity? I'm going to talk about this for a little while, and then hopefully we'll have an answer at the end. But first of all, I have to acknowledge where I am. I have to acknowledge where I am standing, because this is where it starts. This is the motherland. This is the heart and soul of science communication, as far as I'm concerned, because of the people that worked here. This is the desk. This is the lecture theatre. Here, we're in the heart of it all, science communication. And where some of the discoveries I'm going to be talking about actually took place in this very building. So, electricity. What can we know about electricity? Right, well, first of all, electricity is all around us. These lights up here, all of these lights up here are there, and the only reason you can see me is because of electricity. The only reason you can see my slides is because there's somewhere up there, I can't see it because the lights are in my eyes, is a projector which is projecting onto the screen. The only reason you can hear me is because on my bottom I have a battery pack projecting up to Tom up there. And I've got in my pocket, we've all got in our pockets, electricity. We've all got these devices, they're all powered by electricity, they're all connected through electricity and electromagnetic radiation. And in fact, what I'm going to do is, oh, it's just gone to sleep, typical. What I'm going to do is I'm going to take a picture of my lovely audiences. I'm going to go, Tom, can we bring the lights up so that we can see the audience? And we're going to tweet this picture. So if you don't want to be in the picture, you have to close your eyes. So I'm going to take a picture that way, and when I take the picture, you all go, like that, okay? Because that's what you have to do when you're being tweeted. So are you ready? 3, 2, 1. Yeah! Not you lot, because you're not in this one. Oh, we'll just tweet it. So that's now gone out into the ether through the power of electricity. It's disappeared off. So where does electricity begin? What is the beginning of the story of electricity? The beginning of the story of electricity goes back to this bloke. Thales of Miletus. Thales of Miletus was an ancient Greek, ancient Greek. Look at his dates, 600 BC, so over 2,500 years ago. Now, Thales of Miletus discovered something. He discovered that if you take a piece of amber, which is fossilized tree resin, people have probably got it in jewelry. There's probably some amber in this room as we speak, but he had a big lump of it, presumably, and he discovered that if you take a piece of amber and you rub it on a cat, something rather peculiar happens. Well, in fact, two things happen. The first thing that happens is the cat becomes considerably annoyed. Chasing the cat around. The second thing that happens, though, is that the cat's fur stands on end. Now, I mean, clearly it stands on end because it's annoyed, but more than that, the fur is attracted to the lump of amber. It's literally pulled towards the amber. And he thought this was very peculiar. And you have to wonder about Thales of Miletus. You really have to think, why did he do this? Because presumably, okay, so he finds a piece of amber and he thinks, oh, this is very exciting and interesting. And then he starts thinking, well, should we rub it on the desk? No. Rub it on the wall? Rub it on a goat? Cat. Oh, yeah, cat. And he rubs it on the cat, but, why cats? I don't know. I worry about these things. Now, fortunately for us, we don't need amber or cats because, never work with animals and children is absolutely true. So instead of amber, we can use this. This is a piece of polypropylene pipe, 3/4 inch waste overflow pipe from B&Q, to be precise. And this is a piece of fake fur. Okay, you do not need cats, which actually turns out to be quite important. So what you do is you rub one against the other. And this is what Thales of Miletus did. He took his amber, he rubs it on the cat. And you rub one against the other. And if I hold this close to my microphone, which is here, without getting my moustache. Can you hear the little click, 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 clicks? That is static electricity forming on this rod, this polypropylene rod. Now, what Thales and Miletus had no concept about, he thought it was something to do with cats. What he didn't realize was that what was happening is that there were these things called electrons. Electrons, subatomic particles, they're everywhere. They're in all of us, they're in the floor, they're in the walls, they're in the ceiling. Everything is full of subatomic particles, and some of these subatomic particles are called electrons. Now, what happens when you rub this polypropylene rod on the piece of fake fur is some of the electrons in the fake fur are transferred to the rod. They rub off, quite literally, they are pulled off the fake fur onto the rod. So they build up on the rod, okay? And they sit there because the rod is made of plastic, and plastic is a non-conductor. So they don't move, so they are static, which is why we call it static electricity. Static electricity meaning the electricity does not move. That's what it comes from. So now, if Thales and Miletus had been able to do this, he most certainly would have performed this experiment. Unfortunately, the cats got in the way somehow. So what we're going to do is, I need to put that just there. And I've got here a piece of space blanket, mylar film, okay? Just a very thin piece of space blanket. And I'm going to charge up this piece of polypropylene, like this. Get it good and charged. Pop that down, discharge my hand, pick that up, drop this, if I can get it off my finger. Ooh. Nearly. I have to start that again. Bear with me. Oh, everything's falling off. Typical. Right, here we go. Once more, with feeling. Pick that up. That's important for later. We'll try that again. So charge up. Put down. Discharge. Pick up. And this time... Cool, cool. Yes, it is cool indeed. What on earth is happening? So what's happening is that space blanket is actually made of a very thin sheet of aluminium coated onto plastic. And the plastic coating, this is irrelevant, but what's happening is when you drop it onto the wand, some of those electrons sitting static on the wand jump onto the metal. Now, because like charges repel, electrons really don't like each other, okay? They are pushed away from the rod. So it's pushed away because there's electrons on it. And I can drop it and pick it up. And then you drive it back up. Whoop. Takes a little bit of practice. And you can make these. They're just literally, it's just a piece of mylar space blanket, carefully sliced. Yep. And then whoop, to you, to me. Now, Thales and Miletus most certainly would have done this. And it is traditional that if you applaud a demonstration, it's more likely to work. Ah, yes. It's almost as if I didn't have to ask. Oh. There. Oh, thank you very much. Oh, there we go. Oh. It's too breezy in here. I'll put that down. So, we have the beginnings of static electricity with Thales of Miletus. And the thing is, though, nothing really happens for not just decades, not just centuries, but millennia. For thousands of years, nothing happens really in the history of science as far as electricity is concerned. And I should point out that the reason it's called electricity is from the Greek for amber, which is elektros. It all comes together. So not much happens, possibly because of the cat thing, which was confusing. More likely because actually making static electricity, as you can see, you rub, you get a little bit of static. But actually making a decent amount of static electricity turns out to be quite difficult. And it wasn't until a chap came along called Otto von Guericke, who's one of my heroes, but we won't go into him really. He comes along, he invents a machine to make static electricity. And it becomes very popular. And what develops out of this are these things called electrical soirées. So, what we have here is a picture of an electrical soirée, and what you have on the right-hand side is you have the electrician. The electrician who has placed his hands upon what's known as a Hawksby device, which was a slightly later development of the Otto von Guericke's static electricity machine, and it makes static electricity. And what it does is it rotates, okay, and you see there's a big wheel over here, and there's a man behind it cranking the wheel. That turns the glass ball. The electrician has his hands. Now, you should note here that the electrician is not called Bob and has his trousers down here. This this is a very genteel man. He's even got a sword, of all things, by the looks of it. Very posh. Because electrical soirees were the entertainment of the well-to-do. They were the entertainment of the upper crust, okay? And this is because nobody really knew what to do with electricity. It was a bit of fun. And the upper crust were the only people who could afford electricians and who could afford, well, quite frankly, anything to do with having fun in those days. So they're all standing around. You can see the guys on the left-hand side there, that's the upper crust. They're standing, oh, very jolly do, and drinking cups of tea and maybe fine port wine or something like that. And they would come here, places like here as well, and see electrical experiments performed, and it was all the rage. So I wanted to show you some of the electrical soirée experiments, some of these early electricians' experiments. And to that end, I have brought my own static electricity generating machines. Now, I've got two, because I'm sort of greedy that way. This one here is called a Wimshurst machine. And there's a beautiful example out there in the foyer out there. You can have a look at that. It's a really lovely example. This one's completely modern design. And this came out in about, this was the middle of the 1800s, so this is 19th century. Wimshurst. This machine here, though, is the one that you're probably more familiar with. This is called a Van de Graaff generator, which was invented by Mr. Van de Graaff, not particularly surprising. In the 1920s, he was an American, and he built enormous Van de Graaff generators, and this is certainly the biggest one I've ever seen, and I'm quite scared of it. And I should know, because I built it. We have a static electricity generating machine. We build up static on here. The first and most obvious thing you can do with a static electricity generating machine is generate a lot of static and then make a big spark. Because, well, that's what we all want to see, isn't it? A big spark. So, here we go. I'm going to make a big spark, and we'll bring the lights down just a little bit because it should show up slightly better. And we'll see whether this is working for us today. So we're charging it up. I can hear it starting to crackle. Oh, that was quite a big spark, but it wasn't a very juicy one. It's quite a big one. Right, let's try and go for one more. I'm enjoying this, you can tell. Oh, I'm going to stop there before I burn my motor out. Make sure you discharge. So, okay. We can make a big spark. We can make lots and lots of static electricity. And the way this machine works is basically, rather than, it's doing exactly the same as I was doing with this rod. All we're doing is, rather than rubbing like this, we're using a machine to rub, effectively, electrons off the bottom, carry them up, and build them up on the top. And they just pile up on this big dome. And the bigger your globe at the top, the more static you can make. And yes, ladies and gentlemen, those are serving bowls from IKEA. And in fact, that is the entire reason this show exists, because I went into IKEA and I saw them and I thought, oh, I know what I want to do with them. So I built this, and then I thought, now what am I going to do with it? So, yes, anyway. Right, we can make big sparks. Now, the next and obvious thing to do with static electricity is to do what they're doing in this picture here. If you look at the picture here, at the back, there is a lady sort of standing with something in her hand, can't quite work out what it is, but she is being charged up by the electrician. The electrician is passing the charge from his hands. He's got one hand, and I think he's sort of passing it on to his amanuensis, who's sort of standing in the background, and then it's passed, and I can't quite tell what's going on. Basically, they're charging the woman up, which is, let's face it, one of the things they were interested in. What happens when you use this strange electricity? What happens when it encounters people? So, charging up a person. Now, the sparks we were getting off that, I reckon, are in the order of 300,000 volts. About 1/3 of a million volts off this machine. About that big, just about right. So I can charge somebody up with this, but there are two problems. One of them is if you have a pacemaker, it's very bad. And the second one is, but the trouble is most people know whether they have a pacemaker or not. It's not something that you sort of don't know about. You tend to know about pacemakers. And there is another problem, though, and this is that there is a heart condition that is a contraindication for taking a very large belt of static electricity, okay? And I'm not sure how many we've got in here, but there's almost certainly one or two of us that have it, because it's about 1 in 200 to 1 in 300 of the population. It is also completely harmless, I should point out, but it is a contraindication for doing this. I have had a 5-point ECG test to look for this, and I do not have this. So I'm safe-ish as far as, in the broader sense of the word, safe. So I can charge myself up to 1/3 volts, should I so wish. Now, I think we know what's going to happen, because you've probably seen it. And it may come as a surprise that despite having quite a significant amount of hair, my hair is the wrong sort of hair for this. Your hair, madam, would be just fine. No, we won't go there. So instead, I've brought my own hair, so to speak, which we will use. So I'm going to... It's fine. It's not silly at all. I'm going to stand on this IKEA stool. There's a theme here. And I'm going to charge myself up by placing my hand on here. And then, oops, a bit far away. Get a bit closer. Is that good? That's good, yeah. I'll do it like that. I'll do it like that. I'm sorry, turn my back to you. I'm going to charge myself up like this, and we'll see what happens. Are you ready? I hate this. Here we go. Charging myself up. And I can feel all my hairs on the back of my arms standing on end. And is it going up? Yes, is it doing it? Is it good? Is it good? Woohoo! There we go. And the problem is, what do you do now? Because I'm all charged up. And I can feel my clothes are starting to do weird things. So what I'm going to do, I'll let go and turn it off. And then I just sort of have to stand here for a little while. Like that. And gradually, I lose the electricity comes off me, the static dissipates. And I can tell because you can see all the hairs on my arms. If you're close enough, you can see that they're all standing vertically like this. And I can lose this now, thankfully. I know, it's a shame. So that was another thing they were very keen on. They were very keen on that. This is one of my favourites. And this is one that they did, although they didn't do it on this scale. So, pie dishes. Discharge. Yeah. And, yeah, that's the danger of this demo, is forgetting to discharge. Right, so they go on there, like that. Now, the reason my hair stands on end is the same reason, or stood on end, is the same reason that the little floaty thing floats in the air. It's because it's all the same charge. It's all negative charges all over me, all over my hair. So the strands of hair become coated in negative charges. They push away from the other strands, and that lifts them into the air. In the same way that these pie dishes become coated in negative charge. Now the big ones, come on. One more. Hey, 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 yep. 2, 1, yeah! Can you two give me a hand and pick these up? Excellent. That's what I like to see. Putting youth to work. There we go. Brilliant. Thank you. Pick them all up for me. So yeah, so the pie dishes become charged with negative charge. They become very electrically charged. 300,000 volts. The electrons push against each other, pushing away, and it lifts them into the air. Brilliant. A round of applause for my volunteers. They have just about done. Oh, look at that. Genius. Oh, and one more there. I did this morning. They just scrunched them. It was a mess. Right, excellent. So everything we've done so far is about, they're all experiments where things have become charged with the same charge. But you can do something a bit different for that. Now, there was one of these electricians. There was a guy called Stephen Gray, who became quite a popular electrician in the 18th century. Now, Stephen Gray was an interesting chap. He actually was an orphan. It's quite an interesting story, which I'll tell you very briefly. He was an orphan. He was a pauper, and he went to one of the orphanages in the centre of London, which will come to me in a second. And he taught himself science, and he taught himself electrical experimental science and stuff, and he became an electrician, like this gentleman here, and he raised himself up. He climbed the greasy pole of social climbing, so to speak, and pulled himself up by his own bootstraps and became a gentleman through science and the art and science of electricity and the art of demonstrating and the science of electricity. And one of his experiments that he was particularly well known for was this one. This is what is known as the flying boy experiment. Now, what he used to do is he would go back to his alma mater, whose name I have remembered, Charterhouse, poor school, and he would go to his Charterhouse and he would borrow a poor orphan, and he would take the poor orphan with him, always a boy, to the Electrical Soirée. And then what they would do is they would suspend the orphan, no really, they would suspend the orphan from a plank attached to silken ropes. You can see them, silken ropes, insulating ropes. And then they would charge the poor orphan boy up. And you can see Gray's hand coming in at the side, charging the orphan up. So the boy would become charged up. Now, the thing is, he would become charged up with, say, negative charge, so lots of electrons on him, so he's minus, and everything else is, relatively speaking, plus, positive. And like charges attract. So what would happen is that then things would leap onto the boy and stick to the boy. And the favourite thing that works particularly well is feathers, which is what's in the middle. You can see the feathers sort of flying up. They're flying up to stick to him, and they would stick all over the child. You can also do it with bits of foil and stuff like that, but feathers is the simplest thing to do. So I thought we should be doing this in this talk. Now, it's a couple of problems. First of all, it turns out to be difficult to get Charterhouse to lend you orphan boys these days, because they don't do that anymore. But the second thing is, it's also immoral. And you can't get it past an ethics committee. So we can't do that. So I thought to myself, what can we possibly put feathers on? What is the only sensible thing to stick feathers to? And the answer is, clearly, a rubber chicken. So, this is my rubber chicken, and it's called Stretch. Say hello to Stretch, everybody. Yes, now you're talking to a rubber chicken. Good. Excellent. So what we're going to do with Stretch is we are going to charge him up, and we are going to stick feathers to him. And for that end, I'm going to use the second of my static electricity machines, because this machine, this is slightly different to this machine. This machine builds up negative charge. This machine separates charge. And what you end up with is positive charge on one side and negative charge on the other. And it makes nice big fat sparks when I turn it on. It's got two counter-rotating plates, the Wimshurst machine, slightly complicated to explain, in fact, completely impossible to explain, but you get these big, fat, juicy sparks in the middle there. Can you see those? It's actually rather more reliable than these machines. Van de Graaffs are notorious for not working when you need them to, and anybody that works with a Van de Graaff will have a hairdryer about their person, as I do, in the back, because you hair-dry Van de Graaffs. You have to dry them out because they're very susceptible to humidity. These machines, Wimshurst, are a much better bet. So what we're going to do is we're going to attach Stretch to one end of this device here. So, first, I need to give Stretch a conductive coat, which always worries him slightly. So we take Stretch and we wrap him in foil, like this. Yes, we're doing the experiment again. And then what we do is we suspend Stretch from the special feather replacement device. And then we make sure we've discharged. We take these off like so. We attach that to there. So what we're going to do is we're going to attach Stretch to the negative end here, or is it the positive? Not quite sure. It all depends slightly on fate and the day of the week, like that. So Stretch here will become negatively charged. At the opposite end here, I'm going to attach myself, it's only fair, to a bucket of feathers here, and this kind of pointy whiskey thing. Technical term, that. And what will happen, we hope, is when I stand on here, stand on this IKEA stool, so I'm going to charge up the feathers with positive charge. Stretch is negatively charged, and just like the flying boy experiment, what will happen is the feathers should leap across and stick to Stretch, unplucking the chicken. This, ladies and gentlemen, is the most stupid thing you are ever going to see in this lecture theatre, and it pains me to have to do it here, because it is a noble and august place. So, are you ready, Stretch? No, probably not. Am I ready? Yes. Are you ready, ladies and gentlemen? Here we go. Everything wired up correctly? Yes. Turn on. Right. I'm charging up here. We charge up the feathers, and they start to leap. Nearly. Ha. Come on. They're going away from him. That's not supposed to happen. Stretch, feathers, sticking to the chicken, and the chicken has been sort of ish unplucked. And once again, I've trashed the place. Hold on, I'll come around here and turn this off. And now what I have to do is discharge it. And when I discharge, I'm going to discharge the system, and you'll see that a lot of the feathers will fall off because they really are sticking there because of electricity. See that? And I get a little tumbling of feathers. Right, we'll unplug Stretch. So, flying boy experiment, or unplucking the chicken, call it what you will. Oops, sorry. And we'll put him back over here. Now, poor Stretch, indeed, abused and mistreated. So, the electricians of the 18th century and the beginning of the 19th century were very popular chaps. But there's a big question that we have to ask ourselves. And the big question is this. If I was about to give you a big electric shock, which electric shock would you rather have? Would you rather have an electric shock of 300,000 volts and a tiny current? Or would you rather have 240 volts and a current, which is measured in amps, of just 1 amp? So, hands up if you want 300,000 volts. Okay. And hands up if you want 240 volts. I'm not telling you. Either way. And hands up if you really don't want the shock. Please don't do it. Yes. Yeah, indeed. Right. Okay, if you said 240 volts, stand up. Stand up, all the 240 volt people. There's got to be some more of you, some more at the back. We all saw who it was. Yes, stand up, madam, you especially. Stand up, because you're all dead. I'm sorry, but that will kill you. Okay, here we go. Right, everybody. Put your hands around the bottom of your chairs like this. We've wired it all up. Are you ready? On the count of 3. 3, 2... No, I'm not joking. But if I could, I would. Oh, man alive, I would. We are actually going to, for the one show, we're going to try and break the record for the world's longest human electric circuit. But that's another story. Yeah, the thing is, it's current that kills and volts that jolt. That's what you've got to remember. Current that kills, volts that jolt. A single amp of current doesn't seem like much, but it's enough to kill you. And in fact, if you put your finger in the mains, so yes, I am talking about AC, if you put your finger in the mains, you will get 10 amps, something like that maybe, flowing through you, which is more than enough to see the end of you. But the big question is, what is the difference? And this is one of the things that a lot of people just don't have a handle on. What is the difference between voltage and current? Right, let's get some volunteers. What we're going to do, I need a bunch of kids. I need a whole load of you. Let's get all 4 of you, and then can we get some from the row behind? Does any of you lot want to volunteer as well? Yes? Should we get all 4 of you as well? Do you want to volunteer? You don't need to come down. It's a chance for volunteers later. Right, you lot come down here. You lot come down here. Come down here. I'll get you to the bloke in the fly Emirates top, you in the Arsenal. You can come over here. I want you right at the end there. And then the rest of you form a line and take a step forward, sir. And then take a step to that side. And then form a line, because there's quite a lot of you. And what's your name, sir? Max. Max, you are very important. You're the person whose name I am going to remember. So Max, I'm going to put that there. That's important, okay? So what we have here is I have some little glowy-in-the-dark ball thingies. Ooh, that one's flashing. This one's green today, and this one's red. And can we bring the lights down a squeak, please? And what we're going to do is I'm going to pass these down the line, okay? Now, you guys are my electrical wire. You are my copper wire. Are you are or is? I'm not quite sure whether it's plural or singular. And when this electron flows down the wire, we are passing a current. Are you ready? Get in the queue, get in the line. That's it, nice straight line. Here we go. Here comes the electron passing down the wire. The electron goes down the wire. Max, put it in the box behind you. It goes down the wire. We are not passing many electrons. Okay, here comes another one. All right? But what we are doing is we are passing a small current. Here comes another one. But I can increase the current that flows down this wire. Turn some of these on in advance. By passing more electrons down the wire. Are you ready for more electrons? Here they come. Hop. Hop. So now we are passing more electrons. Ooh, turn them on quickly. No, that one's on. And that one on there. We're passing more electrons, which means we are passing more current. The number of electrons that flow down the wire is equal to the current flowing. Okay? So electrons, number of electrons is current. Now, that was going crazy. We'll not worry about that. Now, the thing is, as electrons pass down a wire, they create friction. Just as if you know, when you rub your hands together or whatever it is, you get friction, your hands get hot, yeah? So as the electron passes down this wire, it actually heats up the wire. And if you pass enough electrons, the wire gets very hot. And that's the problem with current. This is why current kills you. It's the heat that it generates. There are a couple of other issues. So what is voltage then? Right, voltage. So far, I'm going to pass a nice gentle current down. Here it comes. Here it comes. We're not doing much work, are you? They're not putting much effort in. I think what we need to do is we need to hold your hands up in the air, up like this, and pass it way up in the air like that. A little bit more effort. A little bit, not much. Now stand on one leg, and do it standing on one leg, with your hand in the air. This is where it gets exciting. And do I dare go the next way? Yes, okay, hop. And now we're going to do this hopping. And we're passing the same amount of current. This one's gone off. But we are doing a lot more work as we pass the current, which means the voltage is greater, okay? The voltage is the amount of work you do as the current flows down the wire. Max, you're not hopping. Right, round of applause for my volunteers. There you go. Thank you. Well done. Here, let me take that one off you. So, current is the number of electrons. Is that still on? Can't tell. It is now. And voltage is the amount of work you have to do to get the electrons down the wire, which is why it doesn't really matter how much work you have to do. So that this machine produces 300,000 volts, and all that really means is that it's got enough energy there to push the electrons through air a distance of nearly 20 centimeters, okay? Because every centimeter in air is about 15,000 volts in dry air. It's probably a bit less here, actually. So this machine's probably running about 200,000, because it's quite humid. Right, where next? So, there is one other question, though, that science hadn't tackled at this point. And we're starting to get a handle on all of this electrical science going on at this time. But the big question that remained unanswered was, what is lightning then? Because lightning looks awfully lot like a spark, doesn't it? When you make a spark in this machine, it looks like a kind of a miniature lightning bolt. And the big question was, is it the same? It was this guy, Benjamin Franklin. We come across Benjamin Franklin. We know who Benjamin Franklin is. Yes, yes, maybe not. Benjamin Franklin is one of the founding fathers of America. He's also a brilliant politician, a fabulous statesman. He's a theologian. He's a philosopher. He's a writer, and he is a scientist. And in 1750, he suggested this experiment to answer the question of, is lightning the same as static electricity? Are they the same? And what he suggested they did is he suggested that you fly a kite into a thunderstorm. And the kite's line will become wet from the rain, so it will become conductive. And then lightning will strike the kite, and lightning will pass down the wire, and you will get electricity from a key that's hanging on the end. You can see a key. And you will prove, beyond a shadow of doubt, that lightning and electricity are one and the same thing. Now, Benjamin Franklin never performed this experiment, which is a good thing, because it's incredibly dangerous. A man called Thomas Francois Dalibard, who was clearly a Frenchman, in May of 1752 performed this experiment just outside Paris. And just outside Paris, what he did was, rather than fly a kite, he erected a very large metal rod into the air, and he put the metal rod into a wine bottle, presumably because he was French, and he had some wine bottles. And then what happens is he waited for a thunderstorm to come near. Now, this picture here, this illustration from afterwards, shows a sort of a lightning bolt in the sky. This did not happen. What happened is, as the thunderstorm came near, he started to get sparks coming off the metal rod to his knuckle. As he presented his knuckle, he got sparks coming off. You always do it to your knuckle because you've got less nerves, so it doesn't hurt so much. Simple. So he said, that's it, right, proof positive, lightning, electricity, the same thing. And that was all the proof we needed. Lightning did not strike. And in fact, they repeated this experiment. Somebody tried to repeat this experiment, a guy called Richmann, who was a German, you can tell, in St. Petersburg the year later, in 1753, he did this, and lightning did strike the metal rod, and he died, because he was standing at the bottom of the metal rod, and the lightning went through him, which is fatal if you get struck directly by lightning like that. So, but they proved that lightning was electricity. So, but that does beg the question of what should you do in lightning storms? I need a volunteer. I need a volunteer who has no shame. Let's have a look. Let's have a look. Young lady, yes, you're in the middle. Do you have any shame? No. Good, come on up. We will discover. Right, you come down, and I'll just get myself ready over here. Right, come on down and come and stand sort of right in the middle, underneath. Yes, that'll do it. No, only joking. What's your name?
Kayla.
Kayla, right, stand there, face the audience that way. Kayla, what we're going to do is a little role play here for us. Imagine you've gone for a walk. You've gone for a nice long walk. You're out in the countryside, huge open fields. Maybe you're in Lincolnshire, something like that, big fields, okay? Nothing for as far as you can see. And you think, it's lovely, it's great here. And then suddenly, a thunderstorm rolls in. It's like in the films, you know, but it comes in and lightning begins to strike in the middle. And behind you and in front of you on the side. Kayla, what are you going to do? What are you going to do? Well, Kayla, you are... It's Kayla, isn't it? Yeah. I'm very bad at names. You are a very intelligent young lady. I can see that. So you brought with you an umbrella because, you know, that seems like a good idea, isn't it? So you put the umbrella up, don't you? Yeah, just humour me. You put the umbrella up, which we know is a bad idea. But why is it a bad idea? Surely this is shielding. These are rhetorical questions. Don't put your hands up. All my questions are rhetorical. Why is it a bad idea, Kayla? This is the reason it's a bad idea. Right, lightning has to jump from kilometres up into the sky, down through air. It takes 15,000 volts in dry air, a lot less in wet air. It's raining, it'll be wet. So maybe 5,000 volts per centimetre. To jump from the top of that distance, which is about a metre, we're looking at maybe what's that? 500,000 volts or something like that. Okay, that's a big voltage. That's a lot of energy we need to push the current through. So if the lightning can go down this metal rod, and that will take no voltage because it's a really good conductor, it's going to do that. So it jumps. Rather than striking here, it will go bzzz, and it will strike here. It will go down the metal. You're actually a pretty good conductor as well, it turns out, because you're full of liquid. So it will go up your arm, through your heart, stop your heart, down, through, out the bottom of your leg. Big, horrible burns, you're dead. The casualty rate here is high. Don't go anywhere, we're not finished. Because, okay, let's try another scenario. Let's imagine that there is a single solitary tree. Yeah, you're looking dubious. But there's a single solitary tree in this huge Lincolnshire field. It's a wobbly tree, which possibly needs a little work, this prop. But anyway, imagine this is a tree, and there's a tree. So what do? You run, you hide, you shelter under the tree. No, it will protect you from lightning. Shelter under the tree for me. Hold the tree in the middle, because it's a bit wobbly. It does genuinely protect you from lightning, because the thing is, if you stand under something very tall, it will protect everything. What you do is you draw a line, 2 lines from the top, 45 degrees down, and if you are inside that triangle, you will not be struck by lightning, because the lightning will preferentially strike the taller thing. So the lightning will strike the tree, and not you. So you won't be struck by lightning. Unfortunately, a lightning strike has approximately 30,000 amps. So all that current flows through the trunk of the tree, and the trunk of the tree is full of liquid. And all of that current, all of those electrons, just like in my wire, heat up the inside of the tree. And all of the liquid boils. And when it boils, it turns into steam. And steam takes up more space than liquid. So it goes from this to this, and the tree explodes. And you die because all the shrapnel hits you. So don't hide under trees. In fact, that's even more dangerous than putting an umbrella up. So what do? Well, you could go and hide in a car, because actually that's a pretty safe bet. You could just stay indoors. That's even better. Although if you are, don't touch the light switches. Because you can, if the house is struck by lightning as you touch a light switch, you could be in trouble. The lightning could short-circuit through you. But this is genuinely what they recommend in the States, where they have a lot more of these big lightning storms. What you need to do is bit of science, bit of biology. There are two electrical organs in you, Kaylee, that are very sensitive to electricity: your brain and your heart. So what we need to do is we need to get your brain and your heart below some other part of your body. So bend at the middle and stick your bum in the air. Right over. That's it. Further. Come on, further. Further. Don't bend. Keep your legs straight. Just go as far down as you can. Come on, I could go that far. God. And at your age. And what you mustn't do is touch your hands on your legs. What you must do is cross your hands over your chest like this. Because now what happens is when the lightning strikes, it strikes the small of Kaylee's back. There. Okay? That is the highest point. And at that point, it then has a choice. It can either go that way or it can go that way. But if it goes that way, there's no path to the ground. So it goes this way, and it goes backwards through her bottom, down her legs, and out the soles of her feet. Kaylee suffers horrible burns, but the electricity doesn't go through her heart, and it doesn't go through her head, so she survives. Round of applause for my volunteer, please. Yay! Back you go. Thank you. So, yes, you can protect yourself, and it's all about protecting your vital organs, because you can recover from a burn, but you can't recover if your brain is scrambled, so to speak. Okay, so we've got to the point now in the history of science where we're pretty sure we understand what electricity is, but it's still really not much use to us. We're still just messing around with silly things and pies and chickens and what have you. How then did we begin to tame electricity? How did we really get onto it? Now, I'm going to tell you about just 3 things. And these are the 3 single inventions that I think are the most important in the history of electricity. And the first is these 2 chaps, or is discovered by these 2 chaps. This is Luigi Galvani and Alessandro Volta. Volta obviously gives his name to the volt, and Galvani, well, he doesn't. But what Galvani discovered, and this was the famous experiment you may have heard, where he was dissecting a frog. And he discovered that as he was dissecting the frog, he was cutting through one of the bits next to the muscle on the leg, and the frog's leg twitched. Okay? And it kind of just spasmed on its own, which was a bit freaky, and he probably ran screaming out of the room, "Ah, zombie frog!" But when he came back, he thought, why is this happening? And it was actually Volta that worked out what was going on, because Galvani got his knickers all in a twist over what he called animal electricity. And what they discovered was that you can make electricity using chemistry. You don't need a static electricity machine. Now, I'm going to switch to my little camera here, and hopefully my computer's got enough juice to do this. So what they did, and this is my little camera here, hello, this is a device here, and I'm going to turn it on. This is a voltmeter, so this measures voltage, and at the moment it's measuring 0 volts. And that's because at the moment it's measuring the voltage between these 2 crocodile clips here. Well, there's a crocodile clip and a piece of copper wire, okay? And there's no voltage. But what my 2 guys, Galvani and Volta, discovered is that if you just take something like, well, an acid, a lemon here, just an ordinary lemon. If we take a lemon and we take 2 different metals, this is copper going in, like that. And this is a nail coated in zinc. It's galvanized. So he did give his name to something. Galvani gave his name to galvanization. But if that goes in just next to it, it's not touching, mind you. So they're separated by a little bit of space. Ooh, you can just about see that. Can you see they're separated? Okay. Ooh, put it down. Separated by a bit of space. If I now attach my other crocodile clip to this, look what happens over here. We get 0.9 volts. So we get nearly 1 volt. Now, this battery here, okay, has 1.5 volts. That's how much voltage it can produce. This lemon is producing 0.9 volts, which is not bad for a lemon, really, is it? And in fact, the key here is it's down to the different types of metal, and it's the fact that it's 2 different types of metal. It's zinc and copper. If I change the zinc, take that one out, if I replace it with this metal, and this is a piece of magnesium strip, okay, so this is magnesium, pop that in here, like that. If I attach now, I get nothing. There we go. I get 1.7 volts. I get nearly double the voltage. And that's because magnesium is a much more reactive element. Okay? So what we have here is we have the world's first battery. And the key thing about batteries is that if you unplug a battery like this, what you have is stored electricity that's doing nothing. It's just sitting there waiting to happen. There's a chemical reaction inside here that's sitting, waiting for us to attach a circuit to it. And as soon as we attach the circuit to it, the electricity starts to flow around the circuit, the chemistry starts to happen. Eventually the chemistry runs out. But the key thing is when you unplug it, it stops the chemistry. The chemistry just sits there waiting. So we have the potential to make electricity, which means that I can take this and I can put it in my pocket and I can wander away. And when I need the chemistry, I pull it out, I plug it in, and Bob's your uncle, I've got electricity. So I don't need a huge machine, I just need this battery. And that is one of the key inventions in the history of electricity. And until we had that, we couldn't progress from these huge machines. And the next thing that comes along, though, I'm going to take that out of the way, like that, comes to this man. We go away from him. I'm going to come to Michael Faraday. Sometime in 1821, Michael Faraday was in the basement here, just downstairs, and I looked at his notebooks just this afternoon with Frank James, the wonderful historian that does all the wonderful history here, and he showed me his notebooks, and in the corner at the bottom of his notebooks is a tiny little doodle, and the doodle is about that big. And what Faraday had discovered was that he was looking at, people had been messing around with magnetism, and they discovered that there was a connection between magnetism and electricity. And they weren't quite sure what to do with it, and they didn't quite understand it. But if I show you what Faraday came up with, he came up with this device. Now, you can see the original in the museum downstairs, which is just astonishing that the original of this is in the museum downstairs. It blows my mind. What he had was he had a Fray Bentos pipe tin. He might not have had a Fray Bentos pipe tin. I think it's actually a little glass bowl. His looked really good. Mine looks rubbish. And in the middle is a magnet. And this is key. There's a magnet here. This is a magnet. There's a Fray Bentos pipe tin. And what we are going to do is we are going to take a big battery, although it's only 12 volts, so it's not kind of super duper. And I'm going to attach the battery here so that the electricity is going to go along this wire up here. So then going to go along this metal wire here. Okay? And it's going to go down this dangly metal wire, this dangly metal wire here, which is free to kind of bounce about. And then what I'm going to do is I'm going to put into this tray salt water. This is concentrated salt solution. Pour that in. And the reason I'm using that is because I need something that's conductive. Now, Faraday used mercury, but they get a bit twitchy if you take mercury out in public, because it's deeply poisonous. So, that's now full of salt water. So the circuit will now continue through the salt water, through the Fray Bentos pie dish, up this wire, and when I connect that to there, it flings around and it begins to circulate. Yes! Look at that! And this, ladies and gentlemen, is the world's first electric motor. Faraday comes up with this through just sheer genius and demonstrates it in this very room to the public. And he shows it to people here in this room, on this table, here in front of an audience like you. And this, now it doesn't look much like an electric motor. I know, we think of electric motors, these great sort of lumps like this, and you put electricity into them. But that's because this is, it's a special type of motor, it's called a homopolar motor. But what it uses is it relies on the fact it takes the core, the kernel of the idea that magnetism and electricity are interlinked. They're inextricably linked. And in fact, in some respects, they are the same thing. And you can't think of them as two separate things. You have to think of them as electromagnetic stuff. And when you get electricity, you get magnetism. When electricity flows through a wire, it turns the wire into a magnet. And because of that, the magnet that's at the bottom flings the wire around and it rotates. And with just a little bit of clever changes to the way things are set up, you can start to turn this into a motor that we would sort of recognize as a motor. And it's a really elegant little demonstration. You can make your own version. I'm going to unplug that because it's not working hugely well this afternoon. Here's a slightly different version, but it's essentially the same. What you do is you take a battery. Here's one you can make at home. Doesn't have to be as big as this. You put on the bottom of the battery one big magnet. These are neodymium magnets. These are rare earth magnets, so they're quite a little bit dear, but you can buy them in sort of Maplin and places like that. And then what you do is you take up a wire, and this wire is curled into a coil, okay? And you push that over the top, so that what's going to happen is the magnet is going to join the top of the battery to the bottom of the battery, where it touches the magnet. And because there are magnets there, and it's got a bit squashed in my bag, but it should rotate. Oops, it keeps falling off. It's quite sensitive. They need to be just tweaked so they're just balanced, and this is hopeless at the moment. But it just flings around like that, just like Faraday's homopolar motor. Oh, come on. There we go. But you get the general idea, don't you? If something doesn't work, it's not science if it always works. So, Faraday comes up with the electric motor. Now, the electric motor, however, was not the first electrical device that really changed the world. The first electrical device that really changed the world was first demonstrated by this man, James Bowman Lindsay, in 1835, in June in 1835, in Dundee at a public meeting. He demonstrated the world's first electric light bulb. A lot of people will tell you that Joseph Swan invents the light bulb. A lot of people will tell you that Edison invents the light bulb. They are all wrong, and they're wrong by at least 10 to 20 years, because this guy, James Bowman Lindsay, demonstrates a light bulb before any of them. He gets no credit. No one's ever heard of him, so I like to trumpet his name. This is what he did. He took a very thin fragment of carbon, and what I've got here is a jam jar, and in here, can you see that? I hold it there. Oops, there. See that little bit between the two metal prongs? There's a thin, thin, thin strip. That's actually a piece of propelling pencil lead, okay? From a propelling pencil. It's made of carbon, graphite. It's all squidged together with a bit of wax. But essentially, we have a piece of carbon there. Oh, I'm flailing all over the place. What I'm going to do is I'm going to pass electricity through it, because I've attached that through this wire here, okay? I'm going to attach that to my battery, 12-volt battery. I mean, it's quite a big battery, I'll grant you, but it's just a 12-volt battery. And I'm going to place it inside here to make a light bulb. And the key thing about a light bulb, though, and this was the key thing that Bowman Lindsay discovered, is that the thing is, do you remember when we passed electricity through the wire? I said it got hot because of friction. This happens to a carbon filament. And if I just attach this directly to the battery, it will get very hot. But the trouble is, it will get so hot, it will glow red hot, and then it will react with the oxygen that's in the air, and it will turn into carbon dioxide, and it will disappear like that. So we will get a brief flash, and it will be gone. But if you then take a vacuum pump, we've all got one of these at home, haven't we? Vacuum vans. Yes. Does it ever see any use? No. Because is there a half bottle of wine? No. Anyway, vacuum pump, by the way, invented by Otto von Guericke. My hero. Anyway, we're going to pump the air out of the jam jar. So we're taking the oxygen out, or at least most of the oxygen, because I can't get it all out. This was the key to it, is to pump the air out from the jam jar. Okay? That should do it. I don't know why I look. Yes, I've got the oxygen out. Actually, I'm just checking to see whether I've broken the filament, which is normally what happens. Right. So, I'm going to put these on, because they're sort of steampunk. Which gives you a clue as to what may happen next. This doesn't always work. And what we're going to do is I'm going to get Tom to drop the lights. And I'm going to gently turn this over. And then when I attach it, give it a breath. There's a whole load of smoke. Oh. It's all very delicate to which way I'm holding it. There's a lot of smoke is made. And actually, that's the wax burning off, which is obviously the problem. If I had just pure carbon there, I wouldn't get that. But it's burning off, and it's incredibly bright. Can you imagine how people would have reacted to this? It's astonishing when you consider that all people have... Oh, it's gone. Oh, no, it's back. No, it's gone. Oh, and everything's getting very hot. It does get incredibly hot, and it's actually what's happened is it's burnt through. Even though there's not much oxygen there, but there's enough for it to burn away. But it's astonishingly bright. Imagine you're sitting there, you're used to candlelight and things like that, and gas lamps and complications like this. Suddenly somebody comes along and says, look, you can take a battery, which we can make, and you can just stick it in the corner, and you can attach it to one of these things that I've built here, and Bob's your uncle, Fanny's your aunt, light, whenever you want it. Flick of a switch, the battery's going to sit there. It's not going to run out because it's a chemical battery. It's not doing anything. But when you need the light, it's there for you. It revolutionized the world, this invention. This is the beginnings, in many respects, of the electrical revolution. All the other devices sort of build up to it, and it's that, really, I believe, that revolutionized it. So there you go. We have tamed lightning. Yeah, it's all done. Oh, very quiet. You can turn that up a bit. We like a bit of lightning sounds. We've gone from cats and static electricity. We've taken the cats and we've gotten rid of the fur, and we've made static electricity machines, and we can do all sorts of silly parlor tricks with it, and we can mess about and we can do fun things like that. But ultimately, it all comes down to making it into a practical purpose. We've got your batteries. We can take electricity, we can store it and carry it around in our hands as chemical energy, so to speak, and use it when we want. We've got motors, we've got lights. That's it. We've tamed, yes? So have we tamed electricity? Yes? No. Maybe is what I'm going to say. I'm not so sure. I'm not so sure because, and this is slightly scary, this is actually the scariest part of the whole talk, I think. Let me tell you about something. Let me tell you about this. This is Mr. Sun. Or is it Mrs. Sun? I don't know. Maybe it's Mrs. Sun. Let's call it Mrs. Sun today. This is Mrs. Sun, or Miss Sun, or Ms. Sun. We don't know. And that is a solar flare spewing out of the sun. Okay? On this scale, if we put the Earth on there, the Earth would be just a pinprick, an insignificant speck of fly poop, right? This huge solar prominence comes off, and when it does, it spews out what's known as a coronal mass ejection, a CME. And when the coronal mass ejection comes off, now imagine this is the sun here, the coronal mass ejection spews off, and it comes off and it squirts into space, and it's harmless. But every now and then a coronal mass ejection will come off the sun, and it will stream across the intervening space, and it will hit the Earth right in the face. Okay? And when it does, bad stuff happens because we are so reliant on electricity. Before the electrical sort of revolution, these things happened, they went unnoticed. Now, when you get a coronal mass ejection hitting the Earth, it's a problem because what happens is all of the wires all around us, here and in the ground and in the air and sort of all over the place, they pick up the charged particles as they're spewing through them. Now, the first coronal mass ejection that we observed, ironically, was one of the biggest. It was called the Carrington event. And when it happened, the only electrical devices were what they call Wheatstone telegraphs, you know, the sort of telegraphs that point to letters. Really simple electrical devices. And when this happened, all the Wheatstone telegraphs, they were all going bonkers, and they were starting to see ghosts in the machine were sending messages. And sparks were flying off the equipment to the operator's hands. And if one of these things hits us these days, it knocks out the electricity. because the power stations can't handle the flow of electricity in the pylons, and all the breakers in the power station go poof and explode, right? If it hits a satellite, it can knock out a satellite, and the satellite just goes and dies. If it's a big enough one, it will completely fry the satellite permanently. Now, we are protecting our systems these days. The important electrical generation systems are being protected from this. So that if we have a CME hit, say, London, for example, you might get the electric back in a day, or maybe 2 days. But just think about life with no electricity for 2 whole days. You certainly couldn't be standing here in the dark without lights. You certainly wouldn't be using your telephones, because even if they survive with battery power, because they might go as well, even if they survive, as soon as the battery's dead, that's it, you can't charge them. So no telephones, so no Facebook, no Twitter, none of that. Worse, your freezer will stop working, which means you will have to eat all of the ice cream. So maybe it's not so bad. So I'm not so sure we've tamed electricity. I think electricity has still got a few surprises for us. We still don't know what to do. Lightning still is a most phenomenal, the most awesome, with the force with the most awesomosity. So, I gave you, the talk was called Zap, Crackle and Pop, and I've given you the zap, hopefully. I've given you a little bit of crackle, and now I want to give you the pop. So the pop is this. This is my homage to the early electricians, the electrical experimenters. This is my homage. Now, one of the things they were particularly fond of is setting fire. What they used to do is they used to like to set fire to brandy glasses. So they would pass around the brandy at the end of the soirée, and they would just set fire to the brandy. But I'm going to set fire to something else. I'm going to set fire to some hydrogen. Hydrogen is a highly, highly flammable gas, and this is a balloon full of hydrogen. So in here, we have hydrogen, and what I'm going to do is I'm going to attach this to here, like that. I'm going to stand that there like that. Now, there's a few things I have to remember to do before I do this experiment. The first thing I have to remember to do is to put on appropriate PPE, as it's known in the trade, personal protective equipment. I won't put them on yet, because I can't hear anything. So, but I'll do that, because that looks silly. Personal protective equipment. So, that's the first thing I have to remember to do. The second thing I have to remember to do is... No, can't remember. Oh, I know what it is. I need to put some oxygen in here. Because remember I said you need oxygen to burn things? In there is pure hydrogen. For safety reasons, I don't add oxygen to it. So in fact, this is, whilst it's flammable, it's not going to burn because there's no oxygen in it. So we're going to put some oxygen in here so that the hydrogen has something to react with when we give it a spark. And what's going to happen is I'm going to use my own body to pass the electricity through me, at great personal pain, I should point out. And I will touch this, and the electricity will run up here. It will jump through a little spark gap in here, igniting the hydrogen and oxygen mix, come back down and go to Earth that way. And, well, hopefully it should make a little bit of a pop. Hopefully. So, a bit of oxygen first, like this. Hold on. Open that, and then oxygen going in. Now, in theory, we need 2 parts hydrogen and 1 part oxygen. Because, of course, when hydrogen burns, it creates dihydrogen oxygen, or oxydihydrogen, or something like that, or water, H2O. So you need 2 hydrogens for every oxygen, and I'm filling again. That should do it. Turn that off, unplug this, like that. Put that over here out of harm's way. Okay, so we've done that. Oh, and the next thing I have to remind you to do is that when I ignite this, you may want to put your hands over your ears. Not yet. So put your hands over your ears. So this is the end of the show. I hope you've enjoyed it. I hope you've had fun coming to the Royal Institution. It is a mecca for science communicators like me. It is an astonishing place to come and visit, and it's a great privilege to stand here and to be able to talk to you guys about about this. And in fact, when I was down in the archives earlier on, there was like boxes full of lecture notes about the history of electricity given by all the greats. So it's quite daunting being here. So hopefully you've enjoyed it. This is the deal. If it goes off, you all burst into a round of rapturous and totally spontaneous applause. And we all can go home with a warm, fuzzy feeling. Okay? So, are you ready? Here we go. I'm going to climb on here, like that. Okay, let me just have a think. I'm going to put my hand on there, and I'm going to touch that on there, and we'll see what happens. Are you ready? Yeah. Can't hear a thing. Here we go. Hands over ears, please. Charging up. Oh, it's going to go. Boom! Thank you very much, ladies and gentlemen. Thank you very much.